Welcome to another Lightblade Learning Lab. Today I think we're starting off on a short series of videos about materials, different materials that we can use and cut on this machine. When I say cut, engrave, damage, I think damage is a good word, because that's effectively what we're doing with this machine. We're damaging material. Now, we've talked in the past about various materials and the way in which they have different, something that I call damage thresholds. In other words, there is a certain amount of energy which, if you exceed, would damage the surface of the material. Now, whether that damage is mechanical damage or some other form of damage like heat, there will be a threshold for each material. And that's one of the strange things about this particular technology, the laser technology, because we've taken it for granted that it cuts, that it engraves, that it does strange things to our materials. But have we really got an understanding of what's going on? That's what we're going to try and uncover in this session. And then we're going to go on to look at how the mechanism by which the laser beam works can damage different materials in different ways. Now, you might imagine that this laser beam is like a hot knife cutting through butter. Wrong. Neither is it like a hacksaw or any sort of saw, where you cut through your material evenly all the way through. These are, I suppose, basically what I would call linear damage mechanisms. They damage the whole of the material at the same time. The laser beam is not like that at all. You can watch it cutting through a piece of clear acrylic and you can see a straight line going through there, and you think that it's a magical hacksaw. I'm afraid it's not. The mechanism for cutting with a laser beam is completely different. Now, when we were doing rotary engraving and we used glass, we touched on the subject of just how it is that glass gets engraved, how you can damage the surface of the glass. And that's basically where we're going to pick up and carry on today, the discussion about the damage mechanism. Glass is just one damage mechanism, along with stone, slate, and other mineral materials, where you damage the surface by effectively stone chipping, but it's a thermal stone chipping as opposed to a mechanical stone chipping mechanism. Then we've got wood that looks as though it's a burning process. I chose my words carefully there. And then we've got other things like this, which is a synthetic rubber or a rubbery type material, which, to be honest, I haven't got a clue how this operates. I suspect this is evaporation as well, but it's one of the products that we're going to test in the next few sessions. Now, we've already spoken of the nature of our beam of light that we're producing, our laser beam, and the fact that it has got a brighter intensity in the centre of the beam, and it disappears away to nothing towards the outside of the beam. But of course we can't see it because it's an invisible beam. So when we look at the beam from the side, here's what we shall see. We shall see a very dense central part to the beam, and the light will be getting fainter as it gets towards the outside. Well, we've also spoken in the past about the energy profile across this beam and the fact that it is this sort of shape. And you can clearly see that from the way in which this colour density changes. Right, so I've got a piece of 3mm plywood which I've got sitting in the laser beam, well away from the mirrors and everything else. I've got the power turned up towards maximum, and I'm going to hold the pulse button on, and we're going to burn a mark on that face. Now, I'm going to have to turn the extraction on because we are going to produce a little bit of smoke. Now, I've stopped on and off, but what I'd like you to see is watch what happens right in the centre of that burn. especially when I stop and the flame disappears. I'll try and blow the flame away so that you can see what's going on. Can you see the intense bright light behind that flame? The intensity of light is so high there that I've actually got those sunspots that you see on your retina. Now, the flame has now stopped. And we've just got the glow. Why is that, do you think? Let's move in and take a closer look. And there's the answer to the question. Look, I've burnt a hole in it. Let's understand what this wood is. It basically is a cellulose material, and it's an organic material which burns, and it burns with a flame at about 300–350 degrees C. And once the organic material has burnt away, what we're left with is this black stuff here, which basically is pure carbon. This centre part has not burnt away, it's actually evaporated away. You can't evaporate wood. Well, true, because wood does not have a liquid phase. It doesn't go from solid to liquid to vapour. But carbon is a rather special material. Carbon exists as a solid material, and at about 3000 degrees C it changes directly from a solid material to a gas and just disappears. Hence the reason we have a hole in there. We've turned the wood to carbon, and then we've supplied so much heat to the carbon at the centre of our beam here, we've evaporated the carbon away. And the other thing that I want you to note about this, although the flame was blowing across this way and we got a little bit of a distortion of our halo over here, what we have got is from the centre we've got a gradual burning process which is from very high temperature to a much lower temperature out here where it was scorching. And as you can see, look, it's gone away to a very faint brown right at the edge where we're just having enough heat to damage the surface of the material. We can almost measure the diameter of our laser beam by looking at the size of this. Although the power is in the middle, there is energy that goes out to maybe 10 or 12 millimeters diameter. Now, we've also witnessed this energy profile in the beam by firing the beam at a block of acrylic. And here we can see the energy density at the centre of the beam is much higher because it's penetrated deeper into the acrylic. We've just witnessed exactly the same thing happening with the wood. This very high intensity part of the centre of the beam has been able to generate huge temperatures, and that's before it passes through the lens. Anybody that's messed around with lighting or photography will understand this colour temperature chart. And it was a scientist called Kelvin who basically realised that the filament in a light bulb glowed at different colours, and those colours were representative of different temperatures. Now, here we're talking about temperatures that are going up into the thousands of degrees Kelvin or thousands of degrees C. They're more or less the same thing with an offset. Let me explain. This same guy was also responsible for determining something called absolute zero. Now, all molecules sit there at room temperature doing this. They've got vibration. And basically the amount of vibration is actually an indication of their temperature. The faster they vibrate, the higher the temperature. Now that sounds like a strange concept, but that is actually what temperature is. And here it's defined, how fast its atoms and molecules oscillate. That's what the temperature of an object is. He took that concept to the opposite extreme and said, well look, if they're doing this at room temperature, there must be a point at which when I lower the temperature, all motion will stop. And that is what absolute zero was defined as. Now in modern day terms, with quantum physics and all the rest of it, they have established that absolute zero, there is still a small amount of motion that goes on. But to all intents and purposes, absolute zero means the atoms are not vibrating. And as you raise the temperature, the atoms vibrate faster and faster and faster. Now that concept of temperature and atoms moving fast was also discussed when we talked about the nature of the laser tube and the mechanism that takes place within the tube itself, and how the nitrogen gets very, very excited by being threatened with 25,000 volts. And if you allow more current to pass through the nitrogen, it gets more and more and more excited. And it can do damage to the CO2 molecules because it's so excited. It's all related to this same concept of atomic motion. So if you can carry forward this idea of vibrating molecules, vibrating faster and faster, getting hotter and hotter, that is basically the mechanism by which the laser beam works. Back to this little picture here, our Mr. Kelvin, working the other way, away from absolute zero, determined that the colour of a filament in a bulb was able to determine its temperature. Now absolute zero was determined as minus 273 degrees C, and so that is where the Kelvin scale starts, at minus 273 degrees C. So these values here are degrees K, Kelvin, and they start at minus 273. I mean, they are degrees C, but they've got this offset on here. So to get them into numbers that we understand, we have to add about another 300, say another 300 degrees C onto these. Well, look at these numbers. These are thousands of degrees C. So another 300 degrees C added onto these numbers is not actually going to give us a great deal of change. But the point that I want you to understand is that we've been looking at colours for our glowing wood up here in this bright yellow to white region, and that is somewhere in the region of anything between 4,000 and 5,000 degrees C. At 3,000 degrees C, carbon will sublimate. It will go directly from a solid to a gas. And so here we've got confirming information that what we're looking at in the centre of that beam, I've got to be very careful what I say here, because the temperature is not in the beam itself, but the beam can, depending on the material that we're firing at, and we fired it at wood, in that particular instance it was able to generate temperatures up in the 4,000 to 5,000 degrees C, because it was hot enough to sublimate carbon. Now that does not mean to say that the beam itself is hot. That is a misconception. The beam is a beam of light and it has no temperature. So how do we get the damage? How do we burn things if there's no temperature in this light? I'll bring you back to this little statement here where it says temperature is actually defined by how fast the atoms and molecules of a material vibrate or oscillate. When this light hits the surface of that material, it could do one of two things. If this is a metallic surface, it will certainly reflect. But of course, like all light, the surface has to be flat to act like a mirror. If it's in any way distorted, the light will disappear off at different angles. Things like gold, silver, copper and aluminium, particularly those four metals, will reflect 99% or better. So they are literally mirrors. Lower grade materials like mild steel, for example, or iron will be somewhere in the region of about 60 or 65% reflective. The other thing that could happen is the light can be absorbed into the surface. Ooh, I've got to be careful about this word absorption because it gives you the impression that the material is like a sponge. Wrong. What actually happens is, just at the surface of the material, there are atoms which will be stimulated, just like when you put things in your microwave and it heats up. That's what will happen here. These light particles are stimulating the atoms on the surface of the material. It's light. It can't penetrate the material itself. It can only interact with a surface. And that's the important thing to remember throughout this. The solid starts to vibrate because it's stimulated by the light. And as we've just discussed, vibration, extra stimulation, heat. Because these materials that we're going to be firing this at are non-metallic materials, they have got very poor conduction properties. They do not transfer heat easily. And this heat builds up on the surface, and because the heat can't disappear, it stays on the surface. And it gets hotter and hotter and hotter. As we've seen in the wood experiment, it starts to glow white hot, and it glows white hot in the center here. Basically the wood has burnt away, but then after that we saw this white glow in the center here, and the white glow was the carbon. It wasn't burning, it was heating up, and it heated up to a white hot temperature where it couldn't resist anymore, and it turned into a gas. And so gradually what was happening is here we get a little bit of erosion in the surface as the carbon evaporates, and it leaves clean carbon behind, and so the light beam stimulates this new carbon that's behind here, and gradually what we've got is a process of erosion, and it eventually worked its way through the 3mm thick material. The important thing I need to stress here is this is not like the hacksaw, this is not like the knife, this is not a continuous process. This is almost like a wood pecking action. It's a gradual erosion process. Even with the very high energy levels that we had here, it took time to burn through the wood. But what we can categorically say is that when we fire this beam at wood, it's capable, because of the carbon content, of generating at least 3000 degrees C. Now the beam itself is not 3000 degrees C, it's just a beam of light. Now if this was just a piece of acrylic, this damage here took place at a much lower temperature than 3000 degrees C, because the threshold, the damage threshold on this material is different to the damage threshold of wood. So every material will react to this light stimulation in a different way. But it is the light stimulation that heats up the material. It's not the light itself that is hot. That's an important concept to remember. We are now going to take that beam and we're going to magnify it. We're going to concentrate it down. And we're going to concentrate it down from 6mm diameter to 0.1mm diameter. Basically we're going to amplify the light at this point, the energy density, to some phenomenal value. And in fact, if we do a very simple bit of maths, you'll find that that is about 3,500 times smaller than that. So we've amplified potentially the ability to do 3000 degrees C's worth of damage. There is a huge amplification of the energy density. Watch very carefully here. I'm just going to do a very simple, very quick pulse. You may or may not have seen what happened there, but let's first of all check. How long was that pulse? Maybe 1/10 of a second? The pulse has burnt right the way through, and here's what the underneath looks like. It's burnt right through it in less than, say, 1/10 of a second, or maybe even less than that. We'll do it one more time. Now if you watch very carefully, you'll see two things happening. You'll see a little bit of a flame coming up where the wood is burning away, but then you'll see this white flash as the carbon evaporates. We've still got the same energy profile. It's just been magnified up to some phenomenal intensity as it's been decreased to 0.1 of a millimetre diameter. The same damage principle is existing after the lens as the one that I demonstrated to you before the lens. And whereas with the unfocused beam it was taking us possibly a minute to burn through this piece of 3mm material, when we amplified the beam it was taking less than 0.1 of a second. This piece of wood is the same piece of wood that took over a minute to pierce through with low energy density. Once we amplify the energy density up, we can do the same amount of work in 1/10 of a second. Time is something that's going to come into our cutting and our engraving discussions as we push on with this subject. Now, we saw that in 1/10 of a second we could burn a very compact little hole through. Let's see what happens if I leave the beam on for about a second. 1 second. We've got our scorch corona round the outside, the same as we did here. We've started to generate additional damage around the outside of the hole, whereas here we had it on for such a short period of time that all we did was to pierce a hole instantly through there, right with the centre of the energy beam, and we didn't get a chance for the lower energy levels around the outside to have any burning effect on the wood. So that's another important lesson I'm trying to get over to you about time. You need just enough time to do the damage that you want to do, and not so much time that you actually cause collateral damage as well. Now these are very important concepts when it comes to understanding the cutting process, because this is effectively the process that causes charring on the edge of your cut. The idea is to cut as quickly as possible with as higher energy level as you can. The way in which the laser beam damages material is a difficult concept to try and describe to you, but I hope that I've broken it down into small enough chunks that, like a jigsaw puzzle, you'll be able to put the pieces together for yourself. The fact that we've got energy density, which causes gradual erosion and not an instantaneous cut. Even that instantaneous 1/10 of a second cut that took place as we burnt that hole through was not an instantaneous pierce. It was still done by exactly the same pecking mechanism. It's just that it happened in such a short period of time that it looked as though it was an instant cut, like a hacksaw or a knife. But it's not. It's a woodpecker, a very fast-acting woodpecker. And that process applies to every material that we're going to fire this beam at, whether we're doing engraving or whether we're doing cutting. We're basically we're going to be damaging the material surface with this high energy beam of light, and it's the interaction of the light with the surface that causes the damage. It causes heating, and that heating causes different types of damage in different types of material. Well, I think that's enough mental gymnastics for today. We've basically talked about the damage process for wood and organic materials in this session, and we've used that as a demonstration of how the laser beam damages material, because it's one of the easier concepts to understand. Now, there are other damage concepts which we'll move on to in future sessions, but they're all based on this same principle. So the hard work is done if you can understand what's been going on today. So thank you very much for your time, and I'll catch up with you in the next session.